Music. Do you know this one?
You're going.
Okay, so last time uh, we were going over a particular application of the singular value decomposition of a matrix. So kind of this last picture that I had shown was the following. So for matrix A, singular value decomposition we found was as follows. And then if we took this matrix U and plotted the vectors U sub 1 and U sub 2 here, and so these here I have the subspaces corresponding to these vectors, so my U sub 1 and U sub 2 axes. The points in question, which I began with, so my data points were as follows. It was, I know it's hard to see, maybe I'll circle them here. So this was one of my original data points. This is another one. This is another one. And here's one more. So there's my 4 data points corresponding to thinking of the columns of this matrix A as being those 4 data points. So there they are. I've circled them in blue. And so these lines that I drew in was meant as an explanation as to what this was showing, right? So intuitively, the idea was that we had a singular value associated to U sub 1, and it being the largest singular value, basically this U sub 1 was telling us the direction in which the data points were the most spread out. And U sub 2 is not necessarily telling us a direction in which they're least spread out. It's just telling us a direction in which they are less spread out than U sub 1. Okay, so this is the picture in question. So I'm going to be returning to this picture again here in a little bit. Also, a portion of this lecture, when I move on from chapter 10, chapter 11 has to do with image compression. So most of the most compelling stuff that I can talk about needs images, and unfortunately, I can't go anywhere and print anything. Campus is closed and all that, so the most convenient thing to do is just to have you guys follow along in the notes while I read and show you, what is being talked about in chapter 11. So chapter 11 is a pretty short chapter anyway, because, like I said, it's just a direct application of singular value decomposition, and specifically for image compression. And once you see a couple of those examples, it's pretty neat and pretty instructive. So yeah, it's much better to follow along in the notes, because it's kind of the only way I can convey this for that stuff. But anyway, we'll get to that later. So like I said, I'll be returning to this picture. So this was the intuitive idea, though, was that this U sub 1, the vector associated to the largest singular value, is telling you the direction in which the data is the most spread out. And then, for instance, say this were a larger matrix, so you had more, so let's say that you had more of these vectors, U sub I, then essentially arranged in the standard way of writing this SVD, basically the columns of the matrix U are being ordered in decreasing significance, where if it's most spread out in the U sub 1 direction, it's less spread out in the U sub 2 direction, and less still spread out in the U sub 3 direction, and so on. Okay, so that's how this goes. All right, so like I said, I'll be using that image multiple times. Okay, so that was the geometric intuition. So then there's the algebra that's going on behind the scenes that really lets us know what it is that's happening here. So one, there is, so this is the algebraic shenanigans behind the scenes. So what is it that's going on? Let's look at the SVD of a matrix A. So I know it looks like this. So So it's U sigma V transpose. I'm not going to go over again all the properties that these have. You can refer to previous video. So A is an M by N matrix, of course. You know the properties of these things. Okay, and so so let's let A sub I be columns of A. If this is the case, then just directly from this decomposition, I can actually write out, algebraically, I can write these columns of A as certain linear combinations. So this is S sub 1, V sub 1, 1, U sub 1, where U sub I is a column of U, plus S sub 2, V sub 1, 2, U sub 2, and so on, all the way down to my kth singular value, V sub 1k, U sub k. So that's the first column of A, and the second column of A is done similarly. So this is S sub 1, V sub 2, 1, U sub 1, plus S sub 2, V sub 2, 2, U sub 2, and so on, all the way out to S sub k, V sub 2k, U sub k. Okay, and I can continue this, of course, all the way out to the A is M by N, so it has N columns. So the nth column then is again S sub 1, V sub N1, U sub 1, plus S sub 2, V sub N2, U sub 2, and so on, all the way out to S sub K, V sub NK. That K looks too much, or that N looks too much like the K. V sub NK, U sub K. All right. Okay. So this is just directly from my singular value decomposition and the typical notation for U, sigma, and V. Okay, so that's how this works. Literally what this means is that I can think of the columns of A as being built out of the columns in U, right? They're written as, forget where these things come from for a second. This is, constant U sub 1 plus constant U sub 2. This is just saying that A sub 1 can be thought of as some linear combination of the columns of U. Okay, and that's completely understandable since this is an orthogonal matrix, so those columns form a basis for Rn. Okay, all right. So comparing this to our geometric notion, or to our geometric picture, why is it that we can say that the data, right? So we're considering the columns. So we were considering the columns of A, our data points, right? Going back here to our example, our columns of A are our data points. So the columns of A can be thought of as being built from the columns of U. They're linear combinations of columns of U. Okay, and so then why is it, right, seeing this written out in this way, it becomes apparent that the most spread out direction is the U sub 1 direction. Well, it's because U sub 1 is associated to singular value S sub 1, which is the way that we're doing it in the standard process, is that S sub 1 is the largest of the singular values, and the singular values are listed in decreasing order. So this is the largest value, and so if my columns of A are built out of U sub 1 and U sub 2, this being the largest value, it is going to contribute more, right, to the spread than this value does in the U sub 2 direction, right? So the idea is, since S sub 1 is larger than S sub 2, the data is spread out more in the U sub 1 direction than in the U sub 2 direction. Okay, that's the idea. All right, recall So recall that we are ordering these in the following way. And all of these, of course, are non-negative. Okay. Okay. So U sub 1 is most important, then U sub 2, and so on. Okay. Now, the idea to verify what's going on let's take sigma and replace some of the S sub I, i.e. the singular values, by 0. Okay. So call this sigma prime, and using this we can compute A prime, which is going to be U and times sigma prime times V transpose. Oh, I'm slightly off camera. This should be the orthogonal projection of the columns of A onto U sub 1 and U sub 2. This is just for our specific example. In general, it would be the orthogonal projection onto the subspace is spanned by the remaining columns. So this is just in our example. Okay, to keep it simple. Okay, so yeah, in complete generality, this would be the orthogonal projection onto the entire subspace spanned by the remaining columns that didn't get zeroed out. But in our example, there's only two columns, U sub 1 and U sub 2, so zeroing out one is projection onto the other. Okay, so how does this work? So returning to our example, so consider our previous example. So the matrix A, reading row wise, is 4, 1, minus 2, minus 3, 1, 1, 0, minus 2. And we found that the singular value decomposition was minus 0.9320, minus 0.3625, minus 0.3625, and 0.9320. So this was found to be U, right? So this was U1 and U2. And our sigma was 5.8550, 0. I know I'm reading column-wise here, so I'm not really being consistent. 0, 0, 0, 0, and I have a V transpose that, in keeping with maybe I should draw an arrow here since I ran out of room. So this is V transpose there. So in keeping with our previous examples, I'm typically not going to write out V. I'm just going to leave it as V transpose. So this was what we had in the previous examples. So setting S sub 2 equal to 0 and recalculating the matrix product. On the right, what do I get? So this is Just copying this. This is, I'm not going to recopy this. I'm just going to say this is, so this is U. So this would be U times 5.855, 0, 0, 0, and then the remaining entries here are zeros times V transpose. What do I get? Well, it turns out that I actually get it. I'm going to write it out in this case. I'm not going to write out the other case. So again, reading column wise. So this is 3.812, 1.483, 1.2060, 0.4693, minus 1.7370, and minus 0.6757. One more column, minus 3.281, minus 1.276. Okay. All right, so this is the result. Now, the idea is to then plot this to see what I get. I'm not even going to draw another picture. I'm going to refer to the picture that I'd previously drawn. What do I get when I plot these 4 data points, right? The 4 data points corresponding to the columns here in this matrix product. So what I get, let me get a different color pen. So what I get when I do this is the following. I get the projection of these points onto U sub 1. Okay, so that's the projection I get. Okay, so going back, I set my second singular value to 0, so I change this to 0 here. And what that results in, if I recompute this matrix, this altered matrix product, plot those columns as data points, what I get is my original data points, except now they've been projected onto U sub 1. So similarly, if I were to replace S sub 1 with 0, so similarly, replacing S sub 1 equals 0 yields projection onto U sub 2. So to see that here, so replacing S sub 2 equals 0, sorry, S sub 1 was 0, is this action, projecting these points onto U sub 2. Okay. All right. So replacing the singular value with 0 is projecting onto the subspace spanned by the remaining corresponding vectors. Okay, so we did it for a simple example just in the plane so that we could actually draw this. But in general, that's what it is that's going on. So one more thing to talk about how to kind of characterize what it is that's going on here. So one more thing. So lastly, we can actually discuss the meaning of the singular values. Okay, so what is it that these singular values are actually telling us? Remember that we actually had a definition for variance that we had made in terms of the singular values. So the idea is that note that since U and V are orthogonal matrices, meaning that their columns are orthonormal, if I compute the square of the norms of each of the columns of A, what do I get? This is S sub 1 squared times V sub 1 squared plus S sub 2 squared V sub 1 squared, and so on, all the way out to S sub k squared V sub 1k squared. And that is true for the norms of all of these things. So this is the norm squared of a sub n is S sub 1 squared V sub n1 squared plus S sub 2 squared V sub n2 squared, all the way out to S sub k squared V sub nk squared. Okay. All right. Okay. So recall our definition of the norm of our matrix. Thus, adding the sums of these squares, that was defined to be the norm of our matrix squared. So this is each of these norms of the columns of A squared. So it's the sum of all these things. But then what do I get here? This is actually just the sum of the S sub i's squared. All right, so adding these together. It's the sum of the squares of all these singular values. But we had a name for that, right? This was the total variance. So the total variance. So this is the total variation of all the columns of A. Okay. All right. So this gives rise to a nice quantity that we're going to use essentially to tell us how much of the variance of a matrix is captured by some number of columns in the SVD. So what is the idea here? So one more thing. If I want to know the total variation in all of the columns of A in the direction of U sub I, this is S sub I squared. Okay. And the proportion of the total variation, I should say, in all of the columns of A in the direction of U sub I is S sub I squared divided by the sum of the squares of all the S sub i's, right? So this is the total variation. Okay. So total variation in the direction of u sub I is s sub I squared, and its proportion as a a fraction or as a ratio compared to the total variation of all the columns, which is just the sum of the squares of those things, is obviously s sub I squared. So total variation in that direction divided by total variation, period. Okay. So you'll see the application of this. So there's a summary of these things. So I don't have enough room here, so I'm going to use a different sheet. So summarizing. First of all, suppose that A has already been broken down into its singular value decomposition. Okay, so part 1, the u sub I, break down the directions in which the data is spread out, being most spread out in the direction of u sub 1, less spread out in the direction of u sub 2, less still spread out in the direction of u sub 3, and so on. So the u sub I break down the directions in which the data is spread out. Okay. All right. So secondly, the order gives the relative importance of the u sub I, i.e. gives the order in which the variance of the data goes from largest to smallest. Okay. So next, in the direction of a vector u sub I as a column of u, the variance of the data is s sub I squared, and the proportion of the total variance of the data is s sub I squared over the sum of the squares of all the other singular values, or of all the singular values, period. Okay. And one more thing. If we replace a singular value s sub I by 0 to form sigma prime and compute a prime from that by using sigma prime instead of sigma. Okay. Then the resulting a prime will be the orthogonal projection of columns of A, those are your data points, onto the subspace spanned by the remaining columns. What I mean by remaining here is all of the columns that are not u sub I, right? So if you replace S sub 1, right, in a matrix that's of a dimension where maybe I have 3 columns of u, then this is going to be the orthogonal projection onto the subspace spanned by u2 and u3. Okay, so that's how this is going to work. Okay, so this is a nice summary of these findings. And furthermore, we can use this to directly write out what it is we mean to find by this, or with this. So this leads to the following. So firstly, we can simplify the data by retaining only the large singular values. Why is that? Well, the thing is that since by this construction the columns of U that correspond to large singular values contain more of the variance of the data than the other columns do, right? And in some cases, the first 1 or 2 columns are going to contain, 99+% of the variance of the data. And so essentially just getting rid of the remaining columns is not going to actually dramatically alter the data. And that's really the entire point of this section when we talk about data approximation, is that we can toss out, for a lot of these things, we can toss out a ton of the data and still basically maintain a picture that's very similar. So this is going to be exactly what we do when we talk about image compression coming up. So that's one immediate application of doing this. So that's the idea. This lets us keep the primary direction of variance of the columns of A. So again, thinking of the columns of A as being your data points, you're keeping the directions in which most of the variance occurs. Okay. Secondly, if we retain only the singular values, say S sub 1, S sub 2, up to S sub j, where j is strictly less than k, obviously. If j were allowed to be equal to k, we didn't really get rid of anything. But if we retain only the singular values up to some j, okay, then the total variance in the data that is preserved is what? Well, this would be the sum of the proportions of the total variance in each of the directions. So it would be S sub 1 squared over the sum of the squares of all the singular values, plus S sub 2 squared over the sum of the squares of all the singular values, and so on, all the way up to adding on S sub j squared over the sum of the squares of all the singular values. So combining this is just the sum of the squares of the singular values up to j divided by the total sum of the squares of the singular value, right? The variance itself. Okay. And then, of course, we can use this to specify what amount of variance we're comfortable with, right? So we can use this to specify retaining a certain amount of variance while simplifying data by removing some singular values. Okay. What I mean by that is you can basically specify the amount of variance you're comfortable with keeping. And once you've done that, then you can decide how many of these singular values you're going to zero out. And then lastly, the columns of the A prime that result will in general be close to the columns in A. i.e., the difference to the matrix norm will be small. So they will be close with respect to this distance. So this is what we mean by data or matrix approximation. We are finding an A prime that is simpler, like objectively simpler in some way, and yet is close to A. Again, you can imagine kind of the best way of thinking about why you might want to do this is the very first application of this that we're going to use, which is image compression. The idea is that you have an image, but you don't have infinite storage. So you don't want to maintain the image as it's given to you. Say it's a really high quality image and you want to compress it in some way. That is, you want to toss out some data that is not that useful to retain some specified amount of image quality while still tossing away enough of the data that you are saving space, right? This is it's kind of one of the best examples of an application of this sort of thing. Okay, so again, we're going to see an example of that later. But before I do that, I want to work out, returning again to this example that we did earlier. So, returning one more time. Returning again to our example. So we have our matrix. Actually, the notes is using a different example. Do I want to return to... Maybe I'll just follow along in the notes rather than going back to our example. So I will scratch this. I'll just follow what the notes is doing rather than going back. This will give you one more example of this. So our matrix A is reading column-wise -1, -1, 1, 2, and 2, 2, which has SVD the following. So this is minus 0.6287, minus 0.7777, minus 0.7777. Last entry is 0.6287. Okay, so that's my U. My sigma is 3.8287, 0, 0, 05840. The last column is 0, and this is V transpose, which I'm not using. So, what are some quantities? So I want to compute some quantities. I invite you to go back to the example that we did earlier and compute these same quantities. So you should do that on your own to test that you know what's going on. So I want to compute a few quantities. Okay, so namely the total variance of the data. So what is this? This is the sum of the squares, the singular value. So this is 3.8287 squared plus 0.5840 squared, which turns out is 15. Okay. So remember, this is my U, this is my sigma, which means this is my U sub 1, this is my U sub 2, this is S sub 1, this is S sub 2. Okay. All right. So the left singular vector of A corresponding to S sub 1, which is 3.8287. The left singular vector of A, this is U sub 1, right? So the left singular vector of A is U sub 1, which is up here. So this is U sub 1, this is U sub 2. Okay. So the left singular vector of A corresponding to S sub 1 captures how much of the total variance in the data? Well, in order to compute this, I would take S sub 1 squared and divide by the total variance. So this captures 3.8287 squared divided by 3.8287 squared plus 0.5840 squared, which is 0.9773, or 97.73% of the total variance in the data. Okay. Oh. So 97.73% of the total variance in the data is captured by this first vector U sub 1. Okay. The left singular vector U sub 2 of A corresponding to S sub 2, which is the other singular value, 0.5840, captures the remaining variance, but just to compute it. So this captures similarly 0.5840 squared over 3.8287 squared plus 0.5840 squared, which is 2.27% of the variance in the data. Okay. Okay. So, intuitively, what does this mean? It means that the data is very spread out in this direction and not very spread out in this direction. Okay, does it have to work out so that it is so extreme in this way? No, of course not. But the way that it works out in the standard process is the total variance of the data in the U sub 1, or the total proportion of the variance in the U sub 1 direction, is going to be more because of how we have ordered the singular values in that matrix sigma. Okay. So, so if I form A prime, which is U sigma prime V transpose by creating sigma prime, which is going to be my matrix sigma set with S sub 2 set to 0. So this is 3.8287 and then zeros else. So by creating sigma prime being this and computing the above product, I get, so you can see this is done in the notes, A prime is minus 0.8841 minus 1.0937, 1.3730, 1.6984, and lastly 1.7683, 2.1873. Okay. Let's compare this with A itself. So here was A, and here's A prime. Now, in this instance, we can actually just look at this and say, yeah, you can kind of see how these are very similar, right? Or maybe, just intuitively looking at A prime and A, you say that these are close. Of course, what we're really interested in is that they're close with respect to this matrix norm, but that's also going to be the case. All right, and what is interesting here is that we rebuilt this A prime only from a single building block vector, right? Only this first vector of sigma prime is non-zero. So we tossed out the remaining one. We only had two singular values. And so this A prime was actually constructed from a single vector here that was non-zero, and yet it is close to our original A in some sense. So what does this mean in terms of efficiency? So what this means in terms of efficiency is that we began with 3 vectors or 3 data points in A. Okay, but it turns out that once we computed the singular value decomposition, we could reconstruct a matrix A prime that was close to A, but we reconstructed it out of a single vector that was non-zero. So rather than needing these 3 vectors, I was able to construct a matrix that was close, in some sense, out of a single vector. Okay, so imagine again as a problem of storing data, right? You've essentially reconstructed the matrix A. You didn't need to store these 3 points. You only needed to store this one. Okay, and from that you were able to construct this A prime that was close in some sense to A. So maybe final summary for this example, we were able to construct a matrix A prime that is close to A in some sense from only a single building block vector. U sub 1 that contained 97.73% of the total variance of the data. Now, again, is it always going to work out that you can construct a matrix that is as close as this A prime is to A using a single vector? No. Okay, but in this example we were able to. This is one particular example. Okay, and so what remains then in chapter 10 that's useful is a couple more computations involving larger matrices, and I'll have you read over the rest of those and see what it means with respect to with respect to data modeling and matrix approximation. There's one more thing I wanted to say, which is also gone over in the notes, which is a question about centering of data. So there is a single homework question that illustrates what it means to center the data, and I'm actually going to assign that as homework later. But for now, basically it's that doing this process, we're assuming that we're centering the data around the origin in some particular way. So as I said, there's a homework question where it'll be made clear exactly what it is I mean by that. But that's pretty much all I wanted to say about the matrix approximation stuff. So if you understand the singular value decomposition, then the process for answering questions about it is pretty straightforward and follows directly from that example I did. So in the couple of minutes that I have left, what I wanted to talk about was the beginning of chapter 11. So for the next few minutes, I'm going to be referring to the notes. I've linked them in the chat for chapter 11. The next lecture will also be me referring to the notes extensively, because both chapter 11 and chapter 12 contain a lot of examples and are mostly concerned with graphical applications. And so what's most important is that you actually see what's going on, and I'm not going to waste your time by drawing a bunch of grids here and coloring them in. That would be stupid. So rather than do that, ideally I would have given you guys handouts in class when we did this so that we could talk about it. But this is the online version of that. And so the idea is, I'd already mentioned that there's this really good example of an application of singular value decompositions, which is image compression and the thought of storing an image. Okay, and so of course you probably are already aware of some of these quantities I'm about to talk about next, but some approaches, and this has gone over, like I said, in the notes. So there's for a color image, you can think of RGB. RGB images, right, are encoded with some integer values, so between 0 and 255. Right, so you have RGB values between 0 and 255. So then your total number of color combinations in that way is 256 cubed, which is a lot of colors. Right, that's a ton of colors. So 256 cubed is the total amount of RGB combinations. So you could also think of a grayscale image where you assign integers between 0 and 255, where 0 is black, 255 is white, and all the integers in between are varying shades of those. Right, there are shades of gray in between. Or you can do something which is exactly what we're going to do to make our computations easier, although everything we do here would equally apply just as well to RGB or to the more complicated grayscale images. But we can consider grayscale images where we're assigning a single real number between 0 and 1, where 0 is black and 1 is white. Okay. So thinking of it like this is going to be simpler for our purposes, so that, and he lists in the notes, like, you don't have to worry about integer truncation or anything like that. You're just gonna we're gonna use this last method that's talked about. That is grayscale image. We're assigning a real number between 0 and 1. So grayscale image, assign each pixel a value between 0 and 1. 0 is black and 1 is white. Okay. All right, so we're storing these images pixel by pixel, right? And this is how we're encoding them. Okay, and so on the next page, this is page 4 of chapter 11 notes. There's first example, which is a grid of just solid black or solid white squares. And so in that example, you have each white square, of course, is going to correspond to a 1, and each black square is going to correspond to a 0. And so why not put this grid? It's a 4 by 6 grid. So why not put this grid as just encoded as a matrix, right? Where ones correspond to the white squares and zeros correspond to the black squares, and that's exactly what's done in this example. So you see the matrix below representing that grid. Okay, and so then what is the intuitive idea here going forward? The idea is that you have an image, right? You have an image that is telling you, or is encoding in grayscale, every single pixel, right, has some value between 0 and 1, and you take that image, you read in every pixel as some value between 0 and 1, that gives you a matrix, and then you apply the singular value decomposition of that matrix. And through this analysis, we saw previously that for the singular value decomposition of matrix, it told you that there was some extraneous info in a way, right? If you were okay with tossing out some of the data to keep, say, 97+% of the variance, then essentially what you have done is you have kept some chunk of the integrity of the data. In this context, we're going to be talking about image quality, right? So you have, in a tiny way, made the image quality slightly less, but the hope is that you have been efficient with how you've tossed this extra data, these extra vectors out, so that what remains is a nice enough image, but it's way more efficient, right? It is way easier to store. There's much less storage required. That's kind of the whole idea with compression of any type, but specifically with image compression, that's exactly what we're going to talk about. Okay, well, anyway, I will talk about that next time. I'm going to upload, I owe you all at least like a lecture and a half where the stuff I'm going to upload. I'm going to upload a lecture on chapter 11 and chapter 12. That'll be a single lecture, and so the next live streamed lecture I will start on chapter 13, I believe. And so the idea is to go fully through chapter 15 and then see what we can do on the other side of it. Because the original idea was to get through chapter 15 and then have some fun. So I'll still try to keep to that. Not necessarily doing the remaining chapters in the textbook, but maybe getting an idea for what you all want to see. So anyway, keep an eye out on Elm's announcements. I know I said that like a week and a half ago, but I'm gonna make the final changes to courses soon. Not just your course, but all my courses. So everything will be settled, including all the homework problems that I assign. So anyway, that's it for now. So I'm looking. Okay, no questions. So anyway, I will see you all later. Like I said, I'll make an announcement when I'm going to post some of these extra lectures, and I'll also make an announcement when I list it'll be on the syllabus page on Elm, so I'll make an announcement where I list all the remaining problem sets that you have. Anyway, so I will see you all later.